are bolted to each of the channels that you see. That channel is then resting on a 3x3 diagonal or inclined tube steel beam. Those tube steel beams are then supported by posts at different heights, as you see, to create the 10-degree inclination. Those posts at the base are then welded to a larger tube steel beam which spans from bay to bay. Now that beam that spans from bay to bay are then supported by 8x8 tube steel columns, which are curved and bent down to this 1.5 inch thick steel base plate. Once the forces are transferred here, let's take a seismic event. When the seismic goes in this direction, we've got two anchor bolts here that are taking the tension, and on this side is the compression. Now these anchor bolts are about 1 and 3/4 inch diameter, and these anchor bolts are embedded down into the column to about this depth. The anchor bolts that are embedded into the column are restrained by a rebar cage and some additional rebars provided by the parking structural engineer records. So that is the basic load path, starting from the panel to the channels to the diagonal tubes to the main 6x beams that spans from column to column, and then from the columns to the base plate bolts down to the structural steel, or down to the concrete pedestal. And then once it transfers to this pedestal, it then transfers the whole entire force into the parking structure level. So that's the basic load path system for our PV.
One of the elements in PV system design is always electrical safety, and it's very critical that we follow the grounding all the way from each modules and each panel. So let's illustrate to you what we mean by that. As you can see from underneath each panel, we have the copper ground wire that is connected to each panel, and just like the electrical power circuits go all the way to the combiner, the copper ground wires connected continuously, linking all the panels, travel through the conduit, go down to the combiner, and from the combiner they go down into the inverter room down below. So the next step in our illustration to you is to walk the path of the current and take you to the inverter room, where the current from each of the combiners that go through the conduits, through the columns, all the way down to the basement of the building, to the ground floor, and travel the path towards the inverter room. Walk with me, I'll show you the inverter room where power coming from the roof actually goes down through the various disconnects, goes to the recombiner, to the inverter, to the transformer, and finally to the electrical room. So, all the power coming from the roof level is coming through the conduit, going to the roof flat, coming up. We have 5 disconnects. Each of the disconnects are controlling the power from 2 combiners coming from the roof level. Each of these are rated at 480 volts. So from the disconnect, power is combined into a recombiner. You can see all the green wires, the white wires, and black wires. Black wires are the positive coming in, which are fused. Each of the circuits is protected by 100 amp fuse. The green wires are the ground wires coming in from the, once again from the roof level. And the white wires, which are the negative conductors, they are coming through and they are not switched. And by code, we cannot switch the negative conductors in a PV project. So one of the things that you will see are the flashing LEDs. What we are doing here is we are monitoring the current from each circuit, so we can actually precisely find out whether each of the circuits is producing the current they're supposed to. And once they're all combined through the common combiner plug, the combined current goes into the inverter. First we have the DC side of the inverter, which is protected by a DC switch. We have the inverter itself. And let's check what the current is right now. What kind of power we're producing. So, since the project started sometime in early March, The project has produced, as you can see, 37,000 kilowatt hours, which is pretty good. Currently we have we're producing 140 kilowatts and ampere rates of about 368 amps. All the data, the current data as well as power data, is actually tracked by the computer system. And we have a large LCD monitor in the campus center so that the students and the faculty can see on a dynamic basis the current power production units. Once the power is converted in the inverter from DC to AC, we have an isolation transformer which converts power to 480 volts AC. From the transformer, we take it back to a disconnect for safety reasons. We have a disconnect before the meter. We have the meter provided by LADWP. We have disconnect after the meter so that in case we need to service the meter, we can throw the two disconnects in an emergency if we need to. And from the disconnect, power goes into the electrical room which is adjacent to the meter. Once the power goes to the electrical room, the power can be fed to the power substation.